Hello Fun Nation, my name is James, checking in here with team number 2910, Jack and the Bot, here at the FRC Championship. And guys, this robot is simply a marvel. There's so much to learn from. They got Mark 5, you heard that right, 5 swerve modules on this robot. There's just incredible arm that they've learned over the years just how to perfect this. They won the Pacific Northwest District Championship, one of the top EPAs in the world. There's so much to discover here on Fun. Here with me I have Kylie, Drew, and Sud here. Let's find out more on Behind the Bumpers. All right, Kylie, why don't you take us through the arm on the Jack and Bot robot? Really just marvelous machine you built.
Yeah, so this year we decided to focus on this concept of like familiarity. And so since in 2023 we built our arm and it worked very well for us in 2023. So we decided this year we were gonna go back onto this idea and use our arm. And so essentially, since we had already used it in 2023, we had already noticed a few of the problems. And so this year we basically made improvements to it. So some of the major differences is basically the added length here. And so in 2023, it was much shorter because we didn't have to score that high, but this year it's much longer, so we have this added length here. And so another thing that's really unique is that our pulley is going the same speed as our e-chain. And so our pulley is going the same speed as our chain. And so we decided that if we can just combine it so that our e-chain it's driven by the chain. So that way it's much more efficient. And when we pull it and extend it, they're going at the same speed. Especially in 2023, originally it was pulled by constant force springs, which is kind of dangerous. And so this is just a much better change. Another thing that we added is we have our gearboxes. Instead of it being up here, we have subset it into our drive base, and that helps with the lower CG, which is really nice. And so we have 3 Krakens each to power the extension and the pivot. And so we have the gear ratio for the pivot is 120.83 to 1, while the extension is around 8 to 1. And so we just have the gearboxes that are sitting in our drive base, and you have the chain that runs over to the sprocket. And so another thing on our arm is our climber. And so our climber is really compact and small because we're using our arm to climb instead of actually having a climber mechanism helping us to climb. And so we have these 2 large black wheels here, and it's allowing us to help us center. And so it's spinning, and when it's spinning, it helps us center with 1 bar of the cage. And what's actually mechanically locking us into the cage are these springed latches. So these spring-loaded latches are the ones that are actually holding us on to the cage. And when we torque our arm down and pivot it down, that's what lifts us up. And our climber that actually is moving with this gearbox down here on our arm, with a chain that runs at the underneath of our arm, it's moving, and it will move down to kind of the pivot point of our entire robot to help us balance ourselves with our center of mass to allow us to be level and make sure that we're not like on one side. And another special thing is simultaneously while we're doing that during our climb, we're also extending our arm a little bit so that these hooks down here will basically hook into a hole cutout in our bumper. And when that hooks, it mechanically locks us in. So even after the buzzer rings, our robot will not relax because it is mechanically locked in. So it ensures that we stay climbed for the 3 seconds after the buzzer.
Wow, right? Like that's just such an incredible engineering decisions and just the creativity in this machine, right? So I want to ask you about the decision to have the climber move. Did you guys originally do that already, or was that kind of an iteration you made on the climber?
No, yeah, so this was actually a decision that we decided to make on our very original version of our climber. It was something that we had already realized and something that we wanted to do. So our climber actually has not really changed a lot from its initial iteration. Oh, except this is actually new. A lot of people have been wondering what this is. This is actually a piece of the algae that we have cut and taped, or zip tied actually. And that is because we were sliding off of our cage bar. And so with this, it's just adding an extra little bit of like friction to help us stay on there. And it's not very aesthetically pleasing, but it works really well.
Well, it fits the theme, and I think I can see the remnants back there in your pit. But moving over to Drew now, I'd like to talk a little bit more about this intake. We've seen other teams kind of getting inspiration from it. It's able to center coral so well and pick it up from all directions. Tell me a little bit more about how you discovered that, as well as some of the other cool features on this robot, like your Mark 5 experimental modules.
Yeah, so at the beginning of the season, we knew that we would need a ground intake because we saw that the game piece was circular and we could probably roll it all the way to the reef. And so in doing that, we got very lucky with our prototyping. This was actually the first prototype that we tried, was this model of intake, and it worked on the first time. So there are 2 sets of vertical wheels and 1 horizontal wheel for the coral intake. And then there's the second horizontal wheel for the algae. And so the coral intake, which I think is the cool part, can take coral in from any angle that it ends up on the ground and put it into any angle that we want it to be on the robot. So we pull it in straight for L2 through 4, and we pull it in hot dog style for L1. And so you'll notice that we have 4 can ranges on the intake. And so based off which can ranges are tripped, the robot detects how the coral is oriented. So we know if it's coming in and it's blocking all 4, but we want it to be straight, we have to move it to the side before we can actually intake it. And if it's coming on the side, but we want it to be horizontal, we can side shift it and slide it all the way over. This is the 3rd iteration of our intake, where we have the 2 wheels powered separately. In earlier iterations, we were powering them together, and we had the different durometers on the left versus right. So it was 2 blues and then 2 greens, and that still allowed us for the side shifting, but it didn't allow us to accurately intake coral for L1. And so that's why we switched to having separately driven intake rollers. And then the other thing that you probably all want to hear about are the Mark 5s. So this is these are right now just prototypes. They have a handful of improvements. One of the ones that I'm the happiest with is that they are fully enclosed. The bevel gears are enclosed, so you don't get any carpet fuzz in the bevel gears or any of your gears. So you can just like load them up with grease and they run really smooth. Another thing is that they don't have belts anymore. They have a big gear instead of the pulley that was originally driving the turreting motion. Changing out the gear ratios is very simple. It's like 5 minutes. You just have to change out the motor pinion, which is accessible without disassembling any of the rest of the module. We switched these in right before Worlds, and they were very easy to set up and like basically just a drop-in replacement. Yeah, we have a clear module right here that you can look at. This is the drive pinion. It's a custom modeled gear that has a cover so that the cover's still intact, but you can pull the pinion out. And this screw you can loosen and move to the different indentations so that it changes the distance between the pinion and the idler gear. And then we'll also have the West Coast Products spiky wheels with custom molded hubs for these modules. And the wheels are a lot wider, as you might see. The billet wheels are 2 1/4 inches wide, and the spiky wheels are 2 inches wide.
Well, Drew, really incredible stuff. I'm excited to see what that does to the whole first landscape and everything like that. The enclosure is going to be really nice. I'd like to shift over now to Stuart here, talk a little bit more about the software that makes this machine tick. Obviously, you guys performing at a really high level. How are you achieving that with this robot?
Yeah, for sure. So, Drew and Kylie talked a lot about these amazing mechanical subsystems that we have on our robot. So I'd like to go over a little bit about how we control them at a very low level. So I know a lot of teams use WPILib command-based to control and organize their subsystems. We actually don't do that. We really want to follow aim to follow a philosophy of like finite state machines with all of our subsystems. So each subsystem is strictly structured as a finite state machine with enum wanted states that can be converted to current states that then apply to that then end up controlling the motors. This is baked in with Advantage Kit abstraction, so then we have automatic logging on all of our subsystems. And another thing we did this year to reduce latency on our main robot thread was to multi-thread logging on all of our subsystems. So obviously we have all CTRE motors, Krakens or X44s, and so what we did was we had the status signal values that pulled the like motor data. We have those being pulled and read on a different thread, and then it's then passed back to the main thread, which can use it for logic. So each of the subsystems is its own finite state machine, and the way you control it is you just pass in like an enum state. You don't say go to this position. You don't say roll at this voltage. It's like, okay, enter the intake state or enter this move to position arm state, right? So then on top of that, the way that we control each of these subsystems and then we kind of string them together to get really coordinated robot action is through something that we call our superstructure. So our superstructure is just a WPILib subsystem that accepts all of the other subsystems on the robot. So like it'll accept, I think it's the arm, which has the wrist, then the intake, which controls the rollers, then the climber, and then the drive base, I think are the main degrees of freedom. So it accepts all of those things, and then what it's able to do is, okay, if we want to do some sort of coordinated action like intake a piece, it then tells each of the individual subsystems what to do in order to make that happen. So it would like, okay, tell the arm go to the ground coral collection pose, and then it'd say, okay, roll the wheels until you have a coral, and then it's stripped, then move the arm. So I think that's one of the really cool things about how we control our code is we have these really organized and defined states. So it's very easy for us to coordinate robot action between all of these different complicated subsystems. And so on top of that, I'd like to talk a little bit about our control scheme, which kind of blends very nicely into this superstructure architecture. So we actually we run a single driver here on 2910, and so like no operator, right? So we use the sticks for like controlling swerve, but what's really cool this year is we made really good use of the back paddles to get the most out of this robot function. So some of these buttons can do 4 different things based on what game piece state we'll call it the robot's in. So I can like take you through each of the bindings. So when we don't have a piece, the right side of this is used for coral collection. So for example, this could be a straight coral collect. This could be a horizontal or hot dog coral collect. This could be a station. This is the station coral collect. And then the left side, left bumper would be ground algae. This would be reef algae. And then those are automated. So then if we end up having a straight coral, these button bindings shift into the different positions on the reef that you can score. So this would be right L4, right L3, right L2, and then same for the left side. And then we have automated L1 scoring as well. And in order to maximize our points that we can score in a match because the reef gets so full, we have automated stacking on the trough. So we can score 6 per face in an organized fashion. So if you pick up the coral horizontal, like Drew was talking about earlier, you can use this button to create like the base of the stack, and then this button to create the top of the stack. And then the last, permutation, if you will, of button bindings is algae. And so when we have algae, we use manual eject for algae. These bumpers are used for scoring in the barge, and then these triggers are used for scoring in the processor. So with that being said, I think you'll notice that like it is just one button to score coral, right? And I think one of the really cool things about a robot this year that has really increased our performance is we have like fully automatic scoring. So what that is you press one button, the robot will automatically drive to the correct scoring position and then eject the piece, and the piece is scored. So I want to talk a little bit about how that happens, and it happens with the help of these 4 limelights that we have here on the robot. So if you think about scoring on the reef as like a problem, you have kind of 2. I'll say we have kind of 2 inputs to our system. So we have what side, like, do you want to score on the left like reef pole or the right reef pole, and then what level do you want to score on? Those are the 2 inputs that the driver provides to the system, and then the system figures out everything else. So the system figures out which rotation to snap to, which position to drive to, and then which arm position to move and when to eject. And so I think the way that we figured that out is really cool. So we have 2 what we call reef selection methods. So one of them is rotation based, so I'll talk about that first. So our rotation based reef selection method, essentially what we do is we say that, okay, the driver has initiated, let's say, a right L4 scoring command, right? And so at that point, let's say the robot is pointed at 0 degrees and we're on the blue lines. So because we can score over the front and back, if we're pointed at 0 degrees, this could mean we're either scoring on the very front face of the reef or the very back face of the reef. So knowing this, what we then say to each of our 4 limelights is, okay, do the front limelights see the tag that's supposed to be on the front of the reef? Or do the back limelights see the tag that's supposed to be on the back of the reef? So based on that, you can figure out, what side the driver's actually trying to score on. And then at that point, okay, it's like, okay, let's say that, the tag was right here behind these limelights. It'll know that, okay, I have to score over the back. So it's going to, hold the current rotation or snap to the, closest 60-degree angle. And then, drive to that position, which is essentially a translation off the April tags pose. Move the arm up to the correct position, and once the drive base and the arm are within tolerance, it's going to automatically eject. This also, one thing that I kind of forgot to mention, so the reason this rotation-based method works is it essentially picks the closest 60-degree angle to choose as the input to the system, and it'll snap to that as well, right? Because obviously if you're at not one of the angles that directly fits on the hexagon, there's not really a reef face that's associated with that. So it snaps to the closest one and then determines the reef face based off of that. The other reef selection method that we have is called our pose-based reef selection method. And so what that does is it takes the current pose of the robot, which we're tracking passively over time using wheel odometry when we're not scoring, and it says, okay, which of the 6 April tags that, of the alliance that I'm on is the robot closest to. And so at that point, you automatically know which reef face you're going to score on. So that's covered, and then obviously the side because that's an input to the system. And then the robot automatically figures out whether it's faster to snap to have the front of the robot snap to face that reef face, or have the back of the robot face that reef face. So that's also fully automated. And so we switch between these 2 methods in a match. They both have different strengths. Rotation based is good when we're doing long translations across the field, and our odometry tends to slightly get off. Whereas pose based is really helpful for if we're trying to really quickly fill up a reef face, we don't really have to worry about getting the robot into the current rotation before initiating an automatic scoring sequence.
Well, Sudhir, in 2910, it has simply been a joy to learn more about your robot today. Thank you so much for sharing it with us. Best of luck at the rest of the championships. It's no wonder that you guys are competing here. Just simply incredible.
Thank you very much. Yep.
Thank you all for watching. My name is James for Fun Robotics Network, signing off.